Okay, in this video, we're going to be looking at percent by mass and empirical and molecular formulas. And our specific objectives will be to define and calculate the percent by mass of individual elements within a molecule, define and calculate the molecular formula of a compound, and define and calculate the empirical formula of a compound. So first of all, let's look at our definitions of what a molecular and empirical formula is. So a molecular formula is the chemical formula that gives the total number of atoms of each element in a molecule of a compound. So for example, H2O2 hydrogen peroxide, that formula tells us that there are 2 hydrogens and 2 oxygens bonded together in every molecule of the compound hydrogen peroxide. And for glucose, we know that there is 6 carbons, 12 hydrogens, and 6 oxygens in every molecule of the compound glucose. Our empirical formula, on the other hand, is a chemical formula that shows the simplest ratio of elements in a molecule of a compound. So for example, our hydrogen peroxide, we can actually simplify down to HO. And our glucose, we can simplify down to CH2O. Because when I look at my hydrogen peroxide up here, it's a 1-to-1 ratio. For every 1 hydrogen, I have 1 oxygen. So I can simplify that down to just be HO. And for glucose, if I simplify this by dividing everything by 2, I see that I have a 1-to-2-to-1 ratio. For every 1 mole of carbon, I have 2 moles of hydrogen and 1 mole of oxygen in glucose. So before I can calculate my empirical and molecular formulas, I have to be able to calculate my percent by mass. So in order to learn how to do that, we're going to look at an example. So example number 1 asks us to find the percent by mass of each element in glucose, which we know is C6H12O6. And we know that glucose has a molar mass of 180 grams per mole. And so when calculating my percent by mass, I'm just going to assume that I have 1 mole to make my calculations really easy. So if I have 1 mole of glucose, I have 6 carbons, which has each carbon has a molar mass of 12 grams. And if I have 6 carbons, I have a total mass of 72 grams for my carbon in 1 mole of glucose. My hydrogens have a molar mass of 1 gram per mole, and I have 12 hydrogens in my glucose, or 12 moles of hydrogen in 1 mole of glucose. So I have a molar mass of 12 grams in 1 mole of glucose, and I have 6 moles of oxygen in my 1 mole of glucose, and those oxygens have a molar mass of 16 grams per mole, so 16 times 6 for my 6 moles of oxygen in 1 mole of glucose, and I get 96 grams. So to find the percent by mass, I have to look at the mass of each of the individual elements as compared to the mass of the overall molecule, or the mass, I should say, of 1 mole of the molecule. So the percent by mass for carbon then is going to be 72 divided by 180 grams. And then I'm going to get 0.40, but I have to multiply that by 100 so that I get a percent. So carbon is going to make up 40% of my glucose molecule by mass. Hydrogen, when I compare its mass to the mass of 1 mole of glucose, I get 12 grams divided by 180, and I get 0.07, but to put that in percent, I multiply by 100%, and I get 7%. And finally, do the same thing for oxygen, divided by the mass of 1 mole of my molecule, and I get 0.53 times 100 is 53%. And to check my answer, my percentages should all add up to 100%. So 53 plus 7 is 60, plus 40 is 100. So when I have 1 mole of glucose, 40% of that mass is going to be carbon atoms, 7% of the mass is going to be hydrogen atoms, and 53% of the mass is going to be oxygen atoms. So now that we understand how to find our percent by mass, we can take a look at finding our empirical and molecular formulas. So remember, empirical is the simpler one, and molecular is the formula that gives us the true number of atoms in a molecule. So below are some steps to finding the molecular formula. So step 1 is to find the molar mass for the empirical formula, the simplified formula. The equation is usually going to give you the molar mass of the molecular formula for you to work with. For step 2, you need to find the ratio between the molar masses of the molecular and empirical formulas. Remember, our molecular formula for hydrogen peroxide was H2O2, but I can simplify that down to represent the ratio of hydrogens to oxygens by dividing both of my elements by 2 to get the empirical formula of HO. So there's a ratio of 1 to 2 between my empirical and molecular formulas of hydrogen peroxide. And then finally, for step 3, we're going to multiply each element in the empirical formula by the ratio to get your molecular formula. So let's take a look at an example to see how that works. Example 2 says that dimethylglyoxine has an empirical formula of C2H4NO and that its molar mass is 116 grams per mole. Well, remember from our steps, we know that this molar mass is the molar mass of its molecular formula, which we're going to need to formulate a ratio between the molecular formula and the empirical formula, because this example is asking us to find the molecular formula. And step 1 in our steps to finding the molecular formula says to find the molar mass for the empirical formula. So I have 2 carbons, each with a molar mass of 12, and I have hydrogens, each with a molar mass of 4 hydrogens. And I have 1 nitrogen with a molar mass of 14 grams per mole and an oxygen with a molar mass of 16 grams per mole. So when I calculate this out, I get 58 grams per mole is the molar mass of my empirical formula. Step 2 says to find the ratio between the molar masses of the molecular and empirical formula. So essentially, I'm going to take my molar mass of my molecular formula and divide it by the molar mass of my empirical formula. So I know the molar mass of my molecular formula is 116 grams per mole, and the molecular mass of my empirical formula that I just found is 58 grams per mole. So 116 divided by 58, and I get 2. So my ratio between my empirical and molecular formulas is 2 to 1. And finally, for step 3, it says to multiply each element in the empirical formula by the ratio to get your molecular formula. So my empirical formula is C2H4NO, and I need to multiply this by the ratio I found in step 2, so I have to multiply it by 2, and I get a molecular formula of C4H8N2O2. So the molecular formula for dimethylglyoxine is C4H8N2O2, meaning that I have 4 carbons, 8 hydrogens, 2 nitrogens, and 2 oxygens in 1 molecule of dimethylglyoxine. But if I was to simplify that down to just get the ratio between my elements, my empirical formula would be C2H4NO. Now that we know how to find the molecular formula, we need to determine how to find the empirical formula. So our steps for finding the empirical formula are below. First, we need to calculate the ratio of elements to each other. We're going to assume a 100-gram sample because it makes our life easy, because then to convert from percent to grams, all we have to do is drop our percent and add grams. And then we're going to convert from grams to moles, because the standard measurement for ratios in chemical formulas is moles. We talk about everything in terms of moles. And then finally, we're going to clean up the ratio, get rid of any decimal points, and make it so that we have even whole number ratios by dividing everything by the smallest number of moles. And this probably doesn't make much sense at this point, so let's take a look at an example to clarify these steps. Example 3 says that isopropyl alcohol is 60% carbon, 13.4% hydrogen, and the rest is oxygen. What is the empirical formula? Well, step 1 says to calculate the ratio of elements to each other by assuming a 100-gram sample and converting from percent to grams. So my carbon makes up 60% of my isopropyl alcohol, but because I have a 100-gram sample, if I have 60% of a 100-gram sample, I have 60 grams. My hydrogen is 13.4% of my isopropyl, but again, since I have a 100-gram sample, I know that I have I can assume that I have 13.4 grams. And finally, my oxygen, they didn't give me the percent of oxygen, but by adding 60 to 13.4 and subtracting that from 100, I can determine that my oxygen is 26.6% of the isopropyl. So again, I drop my percent and make that grams. So now in my assumed 100-gram sample of isopropyl, I have 60 grams of carbon, 13.4 grams of hydrogen, and 26.6 grams of oxygen. Step 2 then tells us to convert from grams to moles. So for my carbon, I have 60 grams. So I do my conversion factor, and in 1 mole of carbon, I have 12 grams. So I have 5 moles of carbon. For hydrogen, I have 13.4 grams. And when I do my conversion of 1 mole to 1 gram, I can determine that I have 13.4 moles of hydrogen. And finally, for my oxygen, I have 26.6 grams times my conversion factor of 1 mole over 16 grams, and I get 1.67 moles of oxygen. So what this tells us is that our empirical formula is carbon 5, hydrogen 13.4, and oxygen 1.67. However, we can't have decimals in our empirical formula. We have to have whole number mole ratios. So step 3 tells us to clean up the ratio and divide by the smallest number of moles. So oxygen actually has my smallest number of moles, 1.67. So carbon, I'm going to take my 5 moles of carbon and divide it by 1.67 to get 3 moles. Hydrogen, a ratio of 3. My hydrogen, I'm going to take 13.4 divided by 1.67, which is going to give me 8. And then for oxygen, 1.67 divided by 1.67, which is 1. So my empirical formula actually is C3H8O for isopropyl alcohol. Finally, for example 4, we're going to look at finding both the empirical and molecular formulas in the same problem. So example 4 asks or states that an unknown compound has the following percent composition: 47% potassium, 14.5% carbon, and 38.5% oxygen. What is the empirical formula of the compound? If the true molar mass of the compound is 166.2 grams per mole, what is its molecular formula? So this is actually a two-part question. First, I have to find my empirical formula, then I have to find my molecular formula. So to find my empirical formula, I have to use my percent mass. So my percent composition for potassium is 47%. But remember, I'm assuming a 100 gram sample. So if I have 40% of a 100 gram sample, it's 47 grams. Carbon is 14.5%, but in my 100 gram sample, I can assume it's 14.5 grams. And oxygen, I can assume, is 38.5 grams. And after I convert from percent to grams, I have to convert to moles. So times my molar mass for each of these. So for potassium, I get 1.21 moles. For carbon, I also get 1.21 moles. And for oxygen, I get 2.4 moles. So at this point, my empirical formula is K 1.21, C 1.21, and O 2.4. But since I can't have decimals, I need to clean this up by dividing by my smallest number of moles, which is 1.21, so that I get a whole number ratio. So this is going to be 1 to 1 to 2. So my empirical formula is going to be KCO2. And now that I have my empirical formula, I need to find my molecular formula, which I need to use my empirical formula to find. So for part 2, I need to follow my steps for finding the molecular formula from the empirical formula. And the first part, or the first step in that process, says that I need to find the molar mass of my empirical formula. And the molar mass of my empirical formula is my molar mass of potassium plus my molar mass of carbon plus my molar mass of my 2 oxygens, and I get 83 grams per mole. And step 2 tells me I need to find the ratio between the molar mass of my molecular formula and the molar mass of my empirical formula. So the molar mass of my molecular formula was given to me in the problem, and it's 166.2 grams per mole, and I calculated the molar mass of my empirical formula, which is 83 grams per mole. So 166.2 divided by 83, and I get 2. So I know that my molecular formula is twice as big as my empirical formula. So my final step is I need to multiply by my empirical formula, KCO2, by my new ratio, which is 2. So my empirical formula is KCO2. My molecular formula is twice as big, so my molecular formula is K2C2O4. So now I've found both my empirical and molecular formulas for the unknown compound in example 4. So now we've looked at how to determine percent by mass and how to use that to find our empirical and molecular formulas for compounds. Bring any notes you have and any questions you have to class, and we'll go over this more there.